I don't really know much to say about it, but maybe we could just read a little bit.
I think we'll have to, because I don't remember enough about it.
Because once you've read a little bit,
do you want to go through the just the algorithmic bits, or do you want to read the actual text? Because not everyone might have the book, so I have to tell people what to look for. Like if you have connection to the internet, you can look up our guest network. You should be able to find the book if you Google Sutton Barto and reinforcement learning, or you could look at incomplete ideas. I think it's on page there.
So if it's so this is a complete sort of change of possible proposed change of plan, but so what I've been doing last week was look at AlphaZero again.
Yeah.
And I have a pretty decent idea of how it works. Although I'm not at the point of actually sort of finalize the implementation, but I implemented multi-college research, and that's basically what it does. So I could talk about that for about 30 minutes, I think, if somebody's interested.
That would be very interesting to hear. Definitely. Okay. Right.
What do you mean?
It's like the policy on the list random.
Initially random, yeah, but you learn.
Yeah, I mean initial.
Yeah. So without anything. Well, I mean the thing is like I haven't actually implemented to the point where I did the function approximation yet. So that's the. Yeah.
Sure. Yeah.
Yeah.
That would be great. Absolutely. Yeah.
So that's slightly different. So that's also planning, but a very particular kind of planning.
Yeah. We have another college research here. That was also in chapter 8. That was.
Yeah, page 1
planning at decision time. That's right. Multi-college research. Yep. 811. And I think we did this one, and then we looked at basically we did this subchapter, and then we looked at AlphaZero straight away. Yeah. It's a very short chapter. In principle, I can just read this out loud if you want.
Yeah. We could also take the AlphaZero paper and just see how.
So, actually, there's a couple of new phrases, and I missed the introduction. So maybe as a warm up, we'll do a couple of those algorithms from the book.
Okay.
Because probably AlphaZero is actually like a combination of a couple of concepts, and let's do at least one for the warm up of the.
I think though, except for Andres, was it?
Yeah.
Except for Andres, I think that hi. All right. Yeah, I think the unusual swell of visitors today is due to the part of their course at uni where they have to visit Lido.
Okay. But so that's some kind of computer science where reinforcement learning is part of the curriculum. Okay, so that's right. Yeah. I missed the presentation.
Yeah.
So.
Right.
Yeah.
Is this useful for you? Don't you think?
Yeah.
Or do we want to go through the?
Yeah. So the only thing how it differs, I guess, in AlphaZero is how specifically they do these steps, but so it's.
Bring it on. Yeah, here's the ball.
But so it's basically right. So first, I should put it into a bit of context. This is the thing that works really well in games. So games like checkers or chess or Go actually. This actually works really well. So then every step is basically you do something, your opponent does something, you do something, your opponent. So in self-play, you've just got player 1, player 2, player 3, mod 2. Player 1, player 2, player 1, player 2.
Yeah.
So that's basically how you set up the tree. So the agent decides what to do for itself for player 1, but then it sort of changes the board over and also figures out what to do for the opponent. which is why you get a really sort of balanced.
Yeah.
They call it the Nash equilibrium.
Yeah.
So I guess one of the first things that just to note is that if you play a game in this way, where you basically take your opponent, where you were your own opponent, you end up sort of, I guess you can prove it, but I don't know how exactly that is done, but that it will asymptotically go to a Nash equilibrium. And the Nash equilibrium is basically the optimal strategy for you, that there's no other strategy that works as well in the context of having other players play their strategy, where everybody sort of plays their own sort of optimal strategy.
There must be an entropy, a related entropy thing in there, right? That the opponent cannot extract more information out of your strategy or anything like that.
Yeah, probably. I don't know much of the details.
It's like your database where we like do the something, perform something task, and at the end we use backup, so we don't lose the data in the future. It's like something database.
I'm not quite sure how that
It's like
works.
AI, it's every time like backing up their data. If we are talking about AI,
So you back up what? Sorry?
backing up the data, because sometimes the system crashed and we
Oh.
lose some data.
I see. So
Like something like
right.
that.
So backup here means something something more specific. And it's, when you back up information on a computer, say, that means something different from here. So here it means that what does this tree mean? This tree means so let's take tic-tac-toe. I've got there's 9 cells here, and so usually like it's player white is the one that starts, and then you've got player black. So in here it's noughts and crosses, but let's just say okay, so just keep it simple. So player 1 can play a cell, right? So that means that in the first move, so let's call sort of the blank state or the init state. Player 1 can do 1 out of 9 moves. So this is the number of moves. So 0, 1, 2, 3, 4, 5, 6, 7, 8 of all of the moves that player 1 can do. Right, so those are all the nodes here. And then let's say I selected 0, 1, 2. I selected this node. Now this has a bunch of nodes coming out. So instead of having 9, you now have 8 because we've got fewer. We've got 0, 1, 3, 4, 5, 6, 7, 8. So these are all the nodes that the next player can play. So this is the white or the and this is the crosses.
One less.
Well, it's got one less.
Yeah, but
Every time, like
7 is the last one.
yeah.
Right, you did
Every
move
time.
two. No, I
Oh, no,
remember.
it's actually the
Choose selected or
You keep them guys.
Yeah, actually.
That's a Python counting thing.
Yeah.
Starting at 0.
So it's like gaming.
I didn't mean to jerk anyone.
No, but
but basically, so the tree that we're drawing here is basically this tree. So you basically, with every move, let's say now I'm doing this. So this is 0, 1, 2, 3, 4. Now I've got another.
So you're sleeping on the previous move from the player.
Now, okay, so what do you use Monte Carlo tree search for? It's basically trying to figure out what is the best out of all of these ways of sort of opening up this tree. So that's what happens here. And you can imagine kind of in your mind's eye actually playing this one and then seeing what would happen when you play that move instead. So that's basically in your mind's eye, that's what multicolored research is. So every starting node doesn't have to be the actual root node, but it can be any other node.
So just a step back, so everything we've done up till now has been like model free. Yeah.
Yeah.
So like we haven't sort of like talked about why we need a model and when it's useful.
Right.
So obviously, so we want a model because then we can imagine what would happen.
Yeah.
So if say we're doing this, if we were model free, we would have to play the game and just play it out.
Yeah.
You know, and if you did a move, then I did a move. We wouldn't ever be able to go back to a move and say, okay, well, what if I did this and what if that? Because we don't have any like model for how the game actually works. We can just play.
Yeah.
So,
So what's the reason why you would want to build a tree like this?
well, I'm just sort of probably for myself, just clarifying like why we need a model is so we can like plan.
Yeah.
So we can, you know, say, oh, okay, what if we actually took this action rather than the thing that actually happened?
Yeah. Yeah. Exactly. Yeah. I mean, so for tic-tac-toe, this tree is actually, this tree is, like all these trees are typically finite, but humongous. But for tic-tac-toe, of course, it isn't, so you can just kind of follow your nose and just keep building that tree. And just keep randomly rolling out. And then,
But we couldn't do that with model free because we couldn't actually go back and then see, well, what if we did this instead?
Yeah.
What would you consider them? Because the agent becomes its own model of the environment, so to speak, because you are reacting to your own play, to your own move.
Yeah.
That's a specific form of the play, right?
But if the model is deterministic, you would go back and do the same, like roll out the same trajectory until the point like you're interested in. The difference is that you like it's this one is not time consuming as opposed to like real
Actual play.
models. Yeah.
And
you know the rules of the game.
Well, that's
Like some kind of algorithm we are using in developing like something.
yeah, so we're basically
Algorithm basically.
we're
Some
kind of
condition and
discussing,
if the condition fulfilled then go to the next step. Something like that.
and then so an algorithm is basically the container, and we're now kind of trying to sort of peek into the container to see like what is actually happening. So what's the thing that picks the next action? Right. So so one of the ways in which you can play is you can just say, let's say there's some value function, and I mean in a certain state, which just means like a certain configuration of the game, and this will approximate the probability of winning, say. Now, let's say we go all the way to the end, and let's say if white wins, the score would be +1, and if black wins, you get a score of -1. So here you, so typically what you're trying to do, so let's say white wins, or not wins, that means that the reward that you get is +1. Now, how you kind of develop this tree is sort of moving up it, where in selecting your actions, so this is say the white. So white wants to actually maximize the sort of the expected reward. So you want to basically maximize Q, where these are all the different actions that you can take. But then here, for the next move, you want to minimize it, because now you're playing from the perspective of black. And then if you keep doing this, you get to, I think they call it minimax strategy, which is basically, which is for a two-player game, it's just the Nash equilibrium.
It's like we are playing role play games in that one. Like player one have some weapons and everything, and they have some kind of hit points, and the another player have also like some kind of that. And one player attacking other player, and they reduce their health point. It's like something like that.
That's basically what it is. Yeah. So the thing that's really nice about it is that it actually is the optimum. So if you keep iterating and you walk through this, then you basically get to an optimum. So that's sort of in very broad strokes what like how this sort of game can be set up. But the problem is, what do you do when your game is just way too complicated to do this? So for tic-tac-toe this works just fine, but for other games it's typically it's very difficult to do. So then typically what you do is you introduce an actor critic. So in the Alpha 0 paper they call it F0. So this is an actor critic that returns. So it gives me the probabilities over the next actions from state S and the expected value. Now the nice thing about this is that at some point when you hit it, so let's say this is a leaf node that we've never seen before. We actually never played a game where this configuration was there. Well, then we say, okay, what we do instead is we're going to use our model. We just say we've got so P, by the way, is just the probabilities of all of the actions to pick. And then V is basically the value that you are expecting to find at the end. So the way, at least in Alpha 0, so I haven't read this chapter, so I don't know to what extent it's like from the textbook and what is from the paper. What you end up doing with every game, with every move, you start at some state, then so let's say that it's just a binary choice in this case. Now from here let's say you start from a state all the way to the beginning of the game. This state, which is just an empty node, you don't know what you can do from this. So the first thing is first you select. So in this case it's trivial because you can only select one, and then you expand. And I'll sort of explain the context of why you're doing this later. But expanding just means, so if this is my state S, and this is my S t plus 1, so then, and these are the different actions that I can take. So the expanding just means like what happens when I pick this node? What are the children of this node that I want to play? And then what I do is while I'm expanding, I find that this is my value, and then I just say my P and my V are whatever my neural net is telling me to do. My function approximator is telling me to do. The same thing here. So these are just prior probabilities of selecting actions. That's all right. This is actually what you do here. So while you expand, you also compute the probabilities over this action.
That guy, is it?
I think this is the next.
The value function, the extra credit? That it?
Yes.
The alpha 0 is in the next page.
Mm-hmm.
Right. There's also another image, but I don't know if it's here. No. But it's great. Okay, so just to go back, what are we doing here? So this is Monte Carlo tree search. What you do in Monte Carlo tree search is you basically have a tree and you've got leaves of that tree. The leaves, basically, you know nothing about. And the goal of Monte Carlo tree search is to figure out actually what happens, like how can I assign value to this node so that I can sort of propagate that value back up the tree. And so Monte Carlo tree search happens in a couple of steps. The first is to select which node I'm going to expand. So select means which leaf to expand. Then I'm going to expand. And I'm going to evaluate with my neural net, my function approximator. So that means I'm going to figure out what are the children, the children. So these are the leaf nodes coming out.
That's this one down here. So we've got D and D in the function here.
Yeah, yeah.
Yes.
Yeah, that's a loss function.
Mm-hmm.
Right, so this is the step that I'm talking about now.
Yeah.
So you expand and then you also calculate. So this is just you put the state into your function approximator, which we'll figure out what that is. And these are the values that you put on the node that you've selected. And then step 3 is to do a backup, which means to take all the values that you've so let's say we're in a situation where now we're expanding. We selected this one. So let's say so this is no longer a leaf node. This is a leaf node. And let's put a leaf node. Let's make that a triangle. So that means it's something that we don't know anything about yet. But we do know that it's connected to this guy. And this is also still a triangle because we don't know. But this one we have selected in the past. Okay. So now what happens when we select? So we take the tree as it stands, and we're going to expand and evaluate. So we say we select this guy, and then this turns into this is still a triangle because that means that we don't know anything about it yet. But a circle means that we do know something about it. In particular, we've got some prior probabilities and we've got some estimate of the value. This is just an estimate. It's pretty shit in the beginning, but eventually it will be something that will become more and more meaningful. So this means expand and evaluate. So expand means find the leaves that come out of here. and evaluate. Evaluate means assigning these values to it. And then the next step is to back up. So that means that you take this value that you've just should stop drawing circles, everyone. That you take this value and you propagate it up the tree. What that means so you get at each edge at the edge of the tree, you've got a couple of values that you store there. So you've got n, which is so the visit count. We've got W, which is the sum of all of the values, including the children, which is the sum of all the values, including all the children. So in particular here, let's call this V naught and this V1 or something. Then if we do so in before the backup, we've got W, let's say state as 0, as 1. And then action, well, whatever that action was, this would have been just V. So that's before the backup. After the backup, so after propagating this value up the tree, are so let's just for comparison also put n. And then after, it looks like so it's the old value plus the new, the value coming from the children, and it will inherit all of the values from the children. And then it also, and also you add the count, so that will be 2 in this case.
Because here it talks about the Q value, here it talks about Q.
I mean, what is V?
So V is the predicted value, so it's sort of the primer of the value.
So I mean, but value you mean like the strict definition of value, right? Like
Yeah, it's
expected return.
it's the expected return from that perspective.
But then this W of S naught A shouldn't it be V1?
Hmm?
I mean, I don't understand how this W S naught A equals V naught initially. Like
Oh, because it was
more,
backed up before.
It's more like Q, right?
Right. So actually, so this is how you will define Q. Q is this is just a way to keep track, because actually what you're interested in is Q.
Okay.
So Q is just W over N. It's the expected reward. So it's just a way of taking the average. This is just a sort of an implementation detail. You wouldn't have to really use W. You could also just update Q, because Q is the thing you're interested in.
Yeah.
But the important thing is that it includes all of the values, also from all the children.
So can I ask that dumb question?
Mm-hmm.
So if this node sums up all the paths below it, so could it happen that, let's say, 5 suboptimal ways of play would outweigh the better individual way of playing in
Yeah.
another node?
Yeah. Yeah, that's why it's important what you do with these values.
Okay.
So later you're going to actually use these values to construct a criterion into the search. So so this selection is actually not done willy-nilly, but it's actually done with a specific criterion. But before I want to say what the criterion is, it's useful to first construct the values that you then are going to use, I think.
Just one more question, just related to the, so at each edge we have this particular V, right? And the way we compute W is basically sum tree, isn't it?
It's what, sorry?
Sum tree, isn't it? Just like when you, I mean,
Yeah.
yeah?
Yeah, you take the sum of all the
Just sum
of
tree.
itself and then also all of the children.
All the node of all the children.
Yeah. And so what you do in practice is you just increment a visit count, which automatically happens when a value is backed up from a child.
Yeah.
Because then you just increment the visit count for each node. So this n is always automatically incremented by 1. So it's always the visit count of itself, including all of the, well, it's a visit count of itself, which is the same as the sum of the visit counts of all of the children.
Ah, I see, yeah. So this W just like all accumulated rewards to go from this state that we have experienced so far. And it's just like how many times you go there.
Yeah,
That's
exactly. So it's basically when you calculate an average, it's basically the sum of a whole bunch of values divided by the number of times you. Yeah.
So in the case down there where you have your 3 triangles, if we had visited all of those, then we would have, let's say, they're all final states, or you would then your n would simply become 3 because you go only one step back from the single triangle. That is your final state. And
so
then the other.
If I take one of these,
sorry.
If I now select.
Yeah, because you have three sort of final child nodes in that layer, and each one of them has to be traced back, right?
Yeah.
Yeah. So how do you know in the case? Well, in the case of this is a triangle, so you haven't explored it yet. But if you were to select those, how do you know that it's a final?
It's not the end of the game.
Yeah, so that it's not, so that you could have actually layers that are different, that have different depths. And what is the depth anyway? Like how far does it go down?
Yeah, so the depth is something completely dynamic. Like you have no, I mean, it just depends on what is selected. So it's kind of a depth first search in a way.
Yeah.
And you expand
In tic-tac-toe, it's I think just everything. No,
it's a basic output what user put on the
just do it all the way to the very end.
if they extend those in 4, 5, 6 up to they want.
And then just like a date
Or is it
going
fixed?
up to the node, to
The
the
whole
root.
scenario is fixed, or there was user don't know about the whole scenario. Means how many of them are until what stage
And
it
it's
goes.
gonna be bad.
The leaf was.
So the leaf is whatever we haven't explored yet, right? But the leaf, I mean, obviously it can also be an end node of the game.
Yeah,
So
exactly.
it can be a terminal state.
Yeah. So here it says 1600 simulations.
Yeah.
So does that mean it'll strike out 1600 times until it finds an end node?
It means it does these 3 steps 1600 times.
Ah, okay.
And so just quickly back up means so updating n and w. Right. So that's what what they call the search. So this is the search part, and then there's also the play part. So the search is sort of these 3 steps, and then it also does 1 step of playing. The cool thing about the playing is that if it plays this node, or let's say we also now know something about this state, so let's call it S2 because it's 0, 1, 2. So now we've got triangles here. if we now play this node, we still have the counts of the subtrees. But if you do this 1600 times, your tree is quite big already. So all you do is you basically just you get to a point where, so this part of the graph, so if I now play and I do this, then this part of the graph just drops off, and then I have the remaining counts from all of the simulations that I've done before. So even within each sort of episode or game, my tree becomes stronger and stronger the longer I'm playing that game.
Yeah, because you're exploring that space and
Yeah.
you get more. Yeah, okay.
Now I haven't said what the selection criterion is.
Yeah.
Since so there's I'll just write it down, and then there will be something in there that I haven't defined yet. So the action that you select is the one that maximizes. So Q, I've said what that is, but I haven't said what U is. So Q is just the average value for that state action pair. But U, I haven't said what that is. So U is this, it's something called PUCT selection criterion, or PUCT algorithm or something. Yeah, so UCT is UCB applied to trees.
Oh, upper confidence tree.
Upper confidence tree, yeah, I guess.
Okay.
And then P is probabilistic.
Yeah.
So P, the P in PUCT stands for the fact that you use, so let's just put we've got a constant, hyperparameter, like we all love. And then, so here we've got the square root of the total count over all the actions, so that's all of the children. And then here we've got the count of the specific child, plus 1 to make sure that it's something meaningful. So this is the search criterion. Is something that if you start searching, you don't really know what this is. So it's basically let's initialize it to 0. And then so really what it's going to favor is going to favor things that on the one hand my prior tells me. So what is my prior? My prior is just whatever came out of my neural net. Remember that my neural net gave us this. So you see that it's quite important that you've got a good function approximator, good active predicate, because otherwise, so it's telling you the prior probability of choosing specific actions. And then this is the thing that isn't exactly what UCB is, because UCB is log, so it's like twice the log of NS divided by N SA, and then the square root of that whole thing. That's the upper confidence bound that you have in UCB. So it's not exactly that, but I don't know what it is. I haven't gotten around to actually figure out why this is a good criterion, but that's what. But roughly, this is like 1 over square root of n times the logarithm, and this is roughly 1 over square root of n. So it's like slightly. I don't really.
If I remember correctly, when we did UCB, we had the same questions, like why do they choose these numbers, and we came up with that's basically a sensible heuristic to do it. It didn't seem necessary to choose this one in particular, so it could just be.
So I think this comes out of a multinomial.
I think it. Okay.
You can derive this.
All right. Okay.
But this, I'm not sure if you can derive it too.
Okay.
The problem is I wouldn't be able to tell you what the derivation is because I haven't seen it.
I don't know mathematically, but someone described it as the most neglected child. Like if you've been in that state but you haven't given this action any love,
exactly.
that's what it is.
Yeah.
But I don't know the specific form.
Okay.
Yeah. So so PUCT.
different
That's basically this thing. Okay, and then so what am I doing when I'm selecting? What I'm selecting is I'm saying I'm drawing from well, not drawing. I'm saying it's the argmax of my PUCT criteria, basically. Okay. Now all of the things are in place. So this thing, every time you do, if you do an expansion, you just calculate this p, and you only calculate it once. So for the rest of that episode, it's never updated.
Yeah.
It's weird.
No.
I see.
Still again? Like, what do you do with the P? For this particular state, I mean, yeah?
So let's say so this is a node for which I know P and V because I've selected it before. Which means that I already have the prior, the P and V.
Yeah.
So once I have the prior, and then I can calculate my U.
Yes.
So you just query your neural net that gives you f theta of s for s1.
Yeah.
And
yeah.
you do that only once, and then that remains.
Yeah. And that's it.
I mean, till the end of the game. For this particular episode.
Hmm?
Yeah.
So is the episode the game or the step in the play?
Episode is a game, I believe, no?
An episode is a whole game. Yeah.
Yeah. So you basically freeze your neural net for the whole game.
Oh.
Well, that makes sense, isn't it?
Well, you can still update it, but but even if it's done, it's probably a bad idea to update it. I do agree with you. But when it's done, so even if you update it, it's like this is done by some moment in time copy of the neural network, and this can be done by another moment in time copy.
True.
Yeah. But
If you changed it, wouldn't you be like, it would be like second guessing itself?
yeah, you
Maybe
can have like weird
should've
oscillations
done
or
that.
something. Yeah.
Of course, because you can't return to that state of the game
Yeah.
again, so it's like you're unrolling time as the tree goes
So
down.
what do I think about this move right now?
Yeah.
Yeah.
And it's only used partially. So it's only used here. But if my Q values become more and more dominant,
Yeah.
which means that like if I get a very high value from this, then my Q values become more dominant, especially if I've seen it too many times already. So then I then
Oh, right. So even if you had looked at this particular state in a simulation, say 3 steps of the game ago, you still wouldn't change the p-value that you get from your function approximator.
no, you would do it with every episode you start anew. So then you calculate your P's and your V's again.
But episode being game,
Yeah.
if you're calculating down like several like in your simulation, if you calculate down several branches of this tree, when you take a step, you only move one, right?
Yeah.
Yeah. So then the next time you were looking down, you would be at a different time step, and then you would still not recalculate your P.
No, you
Yeah.
recycle that. Yeah, that's right. Yeah.
Okay.
Right. So we finally got to the last part of the.
I would have thought that you would keep like, it's similar to an old Q network or something, that you would have like at least 2 networks that you maybe would exchange or keep or something like that. And then
Yeah, but that's more like just a Monte Carlo like estimation, isn't it? Just you do like this 1900 rollouts,
Yeah.
just to estimate the V.
Yeah.
But in order to make it like stable, you want to fix your priors,
Yeah.
which are probabilities of the moves. That makes sense.
So it's more kind of that you bootstrap it, and once that's bootstrapped, you don't change it. Not
That's right.
necessarily.
Yeah, you just
okay.
give it a starting point.
Yeah.
You just give it a starting point to start from.
Yeah.
But this is an exploration term.
Mhm.
If n is large enough, then
Yeah.
it doesn't want to. This is no longer the U term isn't no longer
Yeah.
dominant.
Yeah. Yeah.
Does P get used in Q?
No.
Okay,
No,
so
no. Q is really only just the values divided by the visit counts.
So like at the start of the game, the U term is important, and then as you play more, Q gets more and
Yes.
more important, and U goes down.
Yeah.
Exactly. Yeah.
That's it doesn't really matter.
So about this U component, isn't it also kind of looks like some exhaustive search? Because if the state action wasn't explored, we'll get the bonus from that U, and we will be forced to explore that to actually make sure that there is no prospects in there.
Yeah.
Mhm.
So isn't this like actually exhaustive search, like going through all the options?
It depends. It depends on what the value for C UCT is.
Okay.
So the thing that I don't really like about this way of phrasing it is that this value is actually sensitive to the range in which the actual rewards come in. So this is not a universal constant. You have to pick it every
That's
time.
what you said, hyperparameter.
Yeah, so it's a hyperparameter that you have to tune for each.
Okay.
Isn't it like because you're using P in that part as well? So if the probability's super low, even if you haven't really been there,
Yeah.
like it might just still ignore it.
Yeah, so exactly. So it's a way for your neural net. You allow for your neural net to say actually this is not very important,
So the
or
prob-
it's super important. You know,
Okay.
you allow for your neural net to also have the same.
So yeah, you might not have been there, but if your neural net is saying that it's probably a bad move anyway, it doesn't really give it that much weight.
Yeah.
So does C change from game to game, or more from type of game to type of game? So would you change C from playing checkers to playing chess, or would you change C as you progress through? Because it's like a learning rate, right? So you.
Yeah, it's so from checkers to chess, but then also depending on whether you do. So we think between different games there are different optimal values.
Mhm.
But then even so, there's like the actual sort of tuning version of optimal value.
Mhm.
But then there's also the ugly version, which is like your reward at the end of the game may be 0, or it may be like plus or minus 1, or
Yeah.
0 and 1, or 0 plus or minus 10 or
Yeah.
something, like
Yeah.
whatever. So then that value is actually important for the magnitude of this thing. So
Yeah.
that's the thing that's not very pretty about it, but
Mhm.
that's just a minor thing.
Yeah. And then there's probably like all this force the reward sparsity and that sort of thing that changes your Q values along the way. And yeah.
But right, well that's fine. So okay, so the final step is actually to play, which is really just like you make one move, you take one action. So after doing all of this 1,600 times, you take one step. So and they say it's like 0.4 seconds or something, but I think it's like on a gazillion computers at the same time. But I mean, cool. So what does that mean here? So here it means that you just basically chop off whatever happened there. Why? I'm chopping it off by the priors. The priors, of course, are the key. But you just chop off, and then this all disappears because you don't care about it anymore. Because this is now my next state, and now I'm going to just unroll into the future. So then I'm just going to do that again, and again, and again, and again until I reach, say, a terminal state. So if this is a terminal state, that's
So where do you store W and V as opposed to the neural net for P, V? Are you doing the same thing there? Because you're not querying the neural net every time.
no.
So when do you update and where do you update what?
So you query your So this is where you, so in this step, this is where you query your neural net.
Yeah.
But one thing that I haven't said is what is the actual policy that you use to pick your action, right? Because here, this is not picking an action. This is just looking for actions in your tree.
Yeah.
So take one action according to. So I just sample it from pi given s, which is just so it's just the visit count. I just use the visit count to the power 1 over some temperature divided by some normalization constant. So that's just that's it. That's the policy. So you infer your policy, your behavior policy, the one that you actually follow, simply by looking at the visit counts that you've collected on the nodes.
The idea being that if you visit it often enough, then it's important. Yeah.
Yeah.
But that's not the whole policy, right? It's just part of the policy. I believe, like, if you haven't visited any, like if you reach the leaf node, then this policy doesn't make much sense, does it? Then
so
you need to apply something else.
No, you can. So you don't have to stop when you hit a terminal state. I mean, you typically want to, but I'm not sure. I'm not sure actually. But so this is sort of the. So this is not the final policy that the Alpha 0 engine will run as, because the final thing is just this. That's what we're learning. So these guys, we will use as our ground truth to learn f theta. So this is the thing that you use to learn.
No, you're saying that this is an optimal one, but this can't be.
Well, it's more like a sort of a informed heuristic, right? So it's just, if it wasn't a good thing to either explore or to exploit, then n wouldn't be high.
Yeah.
Yeah, it doesn't want to do it.
No, this one is just like pure exploration policy, right? It doesn't care much about the words and stuff, but just takes an action that has the least that hasn't been taken before, or has
It takes it does the opposite.
Opposite. Yes. So it's a greedy one.
It's greedy, but it's sort of like Boltzmann greedy, right?
Yeah.
So if tau is very small, then this is just a greedy. So if say tau goes to 0, that's the greedy policy. But if for tau, so usually when they at the play step they take tau to be 1. But they also say that in the first like 30 steps in the game they take tau to be 0. So that just it does like it's a greedy thing in the beginning because that's good enough.
But then again, this is n. This is just like a counter, right?
Yes.
So no value, no rewards here. So greedy in terms of visitation, in terms of visits.
Yeah. Well, it's like saying I don't care how you came up with this.
Yeah.
All I see is that you seem to really like this node, so I'll just go there. That's all that this is saying. And then right.
So in this here, the action selection, there is the U component which is related to the count, and then Q. So over the time the more visit the U getting smaller. Yes, that's true.
Yeah. Well, depending on what the prior is, but yeah, generally the more you explore, the lower this thing becomes. So U is just there to say, don't forget about these guys.
Okay. So then it's like better approximates Q, but then Q is not used.
No, Q is not used. Q is only used in the selection. And then, so every time I play, I can put a pi on each node. Because my pi is just what I got here.
But the play is the rollout or the play of the game from the start?
Well, it's just going to the next root node. So if this is the state that I'm currently in, which doesn't have to be the beginning state, it can be any state.
Yeah.
And then I go to the next state, then that is now my root node, but it doesn't mean that it has to be the beginning of the game. It can be somewhere in the middle of the game.
Okay.
And then to play just means like take what you so take all of the counts that you've gathered so far and select a node like that, and then also store the pi values. So what you're doing under the hood is we've got pi 0, pi 1, so basically S0, A0, pi 0, and then got another one, S1, A1, pi 1, and these are the things that I then collect to then, or even actually the values. So then I play the whole game, and this is my experience that I'm keeping in my sort of experience buffer or experience cache or whatever throughout the episode. And then once I actually hit a terminal state for which I get a reward, plus or minus 1, then I can actually start updating this. So the loss.
Oh, so you're not updating literally until you've finished.
Yeah.
Like you're going like full scale Monte Carlo, if you will. Like you're doing a full episode of exploration.
Yeah.
And then you roll it. Okay, I was wondering where.
Yeah, except that the player is also allowed to forfeit. How do you call that? Yeah, forfeit.
Yeah.
Oh.
See, which is confusing to me because what if your value function is just completely off?
Yeah. It's surprisingly human. Yeah.
One question.
Yeah.
After that you expand with the neural network, well, the tree, well, you do the updating. But you update with the, for example, in this case, with the last end value in this part.
Yeah.
For example, for S1, A1.
For n is what?
And the function end, or when you update.
Yeah.
Yeah, for example, you after that you create your tree with the neural network.
Yeah.
Yeah. You're updating the value end and W.
Yeah. Yeah.
With what values in this part? Yeah.
Yeah. Yeah.
Yeah. But when you repeat, how do you know the neural network choose the same way?
It wouldn't. So after the episode is done, then you have to let the neural net evaluate it again.
Okay.
Yeah. But throughout the episode, throughout the game, you just let the values that it predicted just be those values.
No, it makes sense. It doesn't. Repeat the measurement.
So it's just like a forward prop, like
Yeah,
roll
exactly.
out till the very end, and then
Yeah.
like once you accumulated this whole tons of values and
Yeah.
pairs of
Yeah.
values, you just do like
Yeah, exactly.
back to the root.
So at the end, we've got like let's say Sn, An, pi n, and the actual value. I think they denote it Z, and then that is enough to then so that the value that the objective that you're the loss that you're trying to optimize for is actually so it's the cross entropy.
Here's the that's good.
So it's basically the ground truth. Let's just call it pi, where pi dot something like that, and the log of what I predicted. So in state S. And then plus the loss that comes from the value function, but they take the squared error loss, which I think is really weird because the value is like win or lose, so why not just take the logarithmic loss, logistic loss I mean, because it's a very unnatural thing to do here.
And one question more, for each interaction you need to train the neural network each time. And do you know how long is each interaction here in the...
So how long does a game take?
No, for each interaction.
Interaction meaning each loop of the play?
For example, for train model, for train the neural network.
Yeah, but you have to tell me what you mean by iteration. Do you mean like the search plus play loop?
Yeah.
It says.
So it says that this whole search thing, which they do 1600 times, they say it's 0.4 seconds. And then, but I mean, they're basically using a UFO to run this, right? So it's like, it's not regular hardware that
They said they played 4.9 million games of self-play.
Overall.
Yeah.
4.9.
Yeah, over the course of training. But I'm a bit confused. Where was it? Where is it here? Where B is? But ZT is the game winner from the perspective of the current player.
Yeah.
In terms of the min-maxing that you introduced before, hey, how does that? Does that have something to do with Z and B? Because I'm a bit confused. It's the same neural network that's just looking at itself, sort of from up or down.
Yeah.
So I'm a bit confused as to what that means for the update.
Yeah.
So I guess -1 is losing and +1 is winning.
Yeah. From the current player's perspective. So it depends. So when it's a two player game, you can just do the min max. That's fine.
Yeah.
But so if you have multiple players, like of course min max wouldn't work.
Yeah.
What would work and what also still works here is like so let's suppose so it's basically changing the input vector. So let's say I've got this configuration in tic-tac-toe. What I then do is then so this is from the current player's perspective, the current player being, say, knots. And then I just switch the board around to make it look like something from the other player's perspective. So I don't know if this is what they do, but this is what I do.
Yeah.
So then I just turn it into this. And now it's the same board,
Yeah.
but now it's from the crosser's perspective.
Right.
Yeah. I'm not doing chess, I'm doing connect 4 because I thought that's already.
That is kind of cool because it is connected, but it's also disconnected in the sense that you don't get this. You have a bit of a, I guess, shuffling of your input data because you don't have this consecutive, independent kind of. Yeah, it's a bit like shuffling your replay state or experience buffer, I guess.
Yeah.
Yeah, use the same word.
Except that it's more like interleaved in this case.
Yeah.
No,
Yeah.
I see what you mean.
Yeah.
So yeah, and I think it's a really healthy thing to do with your.
Yeah.
I don't know how Go works, but like in chess, like white always goes first. So like if you were swapping the board, you could end up in a state where black had gone first, right?
Yeah. Yeah.
Does it break everything?
But if you do that,
Probably.
yeah.
Yeah, I don't know how. So you would have to do another kind of. So I think the fact that you have to go. Well, so in chess, I think you probably would have to do But even in Go, where it seems to be pretty much symmetric, there's still one player who begins. So you always have a sort of like an unbalanced number of things on the board. But yeah, I don't know. I just hope that my neural net doesn't care about it. But yeah, it's really tricky because if you do it like this, you have to keep track of all the minus signs when you roll up. So it's also pretty painful. But I think I managed to do it. But yeah.
So for multiple player, you can use an array for that.
Yeah.
Multi-for.
Yeah. So that's. So I was about to implement that, and then I figured that I didn't want to do it. But basically, where you have your reward that comes from your environment, where you just kind of roll it every time. So you roll it in one direction, and if you roll it up the tree, you roll it in the other direction. If that makes sense. So this is an array of rewards for the current player and then for the other players. And you keep rolling it so that the first one is always the one for the current player. Yeah, but right now I didn't want to deal with that.
For chess, we can do like first two state was fixed, and after third state we start from both sides.
From both sides?
Yeah, means like if we are talking about chess, then always like first white one was first, right? So we can do like first in each state, then white one start, and then go home again in any direction.
So I think the main thing that I worry about is not necessarily who starts, although it definitely does change the value. But what I worry about is the actual symmetry of or the asymmetry of your king and queen. So, but I think that what you would have to do to map this to the other player, I think you would have to just mirror it in the middle.
Yeah.
And maybe that's
Chess is not possible.
As a
with
bishop,
this
I can't remember. As a bishop, some different squares, but each side
Yeah,
on the same side.
Is that
Yeah,
possible? It's not possible, I think.
No, yeah, but then you would have to change
Yeah.
the squares as well.
Yeah.
Yeah.
So it's not possible with this algorithm. Basically, it's need to develop different.
No, I think you can. I think you can.
These are complicated.
Well, yeah, but I mean, just because something.
Because if the rules was fixed on that one.
Nah. Yeah. Exactly. No, because what I said is just like if you flip it in the middle, then you basically turn a black
Yeah.
board
Black,
into a white.
white.
Yeah, I think it could be fine. But anyway. But then you always have the problem still of like at some point somebody starts, and so you always have some sort of asymmetry there. I don't know. I just hope that doesn't really kill my.
Well,
It's also
that's
some
why you
condition
run
other
5 million
conditions.
times.
You need a million GPUs.
It's also some condition the part of that, like timing and all things.
What's that? Sorry.
Like fixed timing. If that move was not made until this time, the other player was lose the game.
Well, yeah. There's always okay. You can always just go into the weeds of making the game more complex, but yeah. No, I'm not so interested in that. But alright. So then the final thing, the final thing that the actual agent, the AlphaZero agent, plays. That's just P and the value coming from this function approximator, where this is sort of the optimal point. So this is the sort of the end state of the algorithm. So that means that
Why not just argmax of V? Or why not greedy? I mean, what's the policy? What's the policy of the trained agent? Isn't it the greedy one? Got to be. No?
don't know.
It has to do with the tree search during the game.
No,
Yeah.
no,
That's the
it's
thing.
just based on
so
the
AlphaZero
prediction.
doesn't do that.
Yeah.
Yeah, that's amazing, right? What it does instead is it uses 40 layers to actually train this thing. But still,
Right.
so it really just uses this. So my policy in the
No,
end
it does use V.
is Well, it uses V because it's nice to see how well you're doing at the moment, but that's all you use V for.
Really?
Yeah.
So you're saying that
So
it uses like the actual train policy instead of greedy one?
Maybe. I don't know. So I don't know if so basically you're asking, does it do this or does it do the argmax?
Of V, yeah.
Yeah. No, what of P?
Of V.
No, V is just a value. That's a
Oh,
scalar.
yeah, true, yeah.
But this is a vector over the actions. But yeah, so what you're saying is like, does it select the actions greedily or does it select it according to the, I don't know. Actually,
Okay.
I don't know.
And just one more question,
My
just
guess is that
to
it's
make clear,
probably
with
good
the
sample.
with the Z values, like let's imagine that we finished the game, right? We got our reward, +1, -1, whatever.
Yeah.
And then we update, and then let's say our trajectory was like over like 100 steps, so we got 100 predictions of our neural net, right? Even more because we do 1600 those simulations.
Yeah,
So we
yeah.
got the whole bunch of predictions and just one reward. So do we use this reward just to apply just to the root node, for example, or we
No, for the entire tree.
for the entire tree?
Yeah.
How do you do that? Like,
So
do we use the same reward for every
Yeah.
single node?
Yeah.
That's
So it's basically just taking your gamma, right? Your discount factor to be 1. That's what we always do. I mean,
doesn't look smart to me. Does?
I don't know. So I to be honest, I'm completely new to all of this game stuff, so I don't really know. So this apparently is a very, very simple algorithm compared to what people have tried before. So I mean, I already felt like, so this took me about 2 days to fully sort of grasp even just what they do, not like what other things you can do as well, because like I feel like the space of different games is just massive. I don't know how to. But anyway, yeah. So what I think is cool about this is that your function approximator is the end product.
Well, that's the whole point.
Well, but that's not what. So the first alpha Go didn't do that.
It was a tabular one, right? It was just like.
I don't know exactly, but it still did search and planning like while it was playing.
While
They
playing.
had like 2 networks, like one to evaluate like how well it was going, and then one to like actually pick the policy.
Yeah.
Well, this one just the same kind of. It just estimates value and gives a probability. So like,
Yeah, but I think it would pick from something like this mixed in with what the prediction was. So with like some sort of like linear combination of I think.
So
Or again, I don't know because I'm all new to this. Yeah. So yeah, that's alpha 0 as far as I don't know. So I don't know.
So have you implemented all of it already? So this is
No, so I've implemented this and this. So what I have to do next is the actual rolling back up. But that should be alright. The thing is, like I'm doing yet another refactor.
Oh.
But this time I think it's actually really the final refactor until like.
sure.
Anyway,
Sure.
Yeah. But so that's sort of how I got stuck. So I'm at this point, and now I wanted to do this, and then I found that actually the way I did my sort of function approximators could be a lot better. So then I started refactoring that, and then so this is still sort of on my
I
on my
have
stack.
like 2 questions that come to mind with that. One, you're doing this for Connect 4 at the moment, right?
Yeah.
What is it? I'm sorry, interrupting you. I don't know what the game is.
It's
Oh,
just
Connect 4 is. Yeah, you probably know it, but it has a different name in every language.
So
Is
let's
it 5 or
say
6
0,
or?
1,
Yeah.
2, 3, 4, 5, 6. Sorry, 5, 6, 7. No, wait,
Yeah.
6. So it's seven slots, and then it's 6 tall. And what you do is you put one. So if you act 3, you end up here, and then I don't know. I do this. You do this.
I got it. I don't know this game.
So 4 in a row.
Yeah.
Jesus.
Yeah.
Didn't know about this one.
Huh?
Never heard of this one.
Oh.
No, 4. Okay.
Yeah.
Yeah. In Dutch, it's like the Dutch equivalent it would be 4 in a row.
Yeah. And so so 2 things that I wanted about. One, if you wanted to expand, I don't know if there's a Star Trek version of Connect 4 where you have a 3D Connect 4. But if you were to make this a box and you were to expand, say,
There is a 3D.
There is a 3D Connect 4.
Yeah, yeah.
Okay, fine. That should be, yeah. And you play that with 6 players or with?
No, just 2.
Just
but
2.
It's so it's a 4x4x4 cube.
Oh.
So it's basically like this, and then.
Yeah. Yeah. Okay.
Or,
Yeah.
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 And then so it's basically spikes, and then you put beads on this.
Oh yeah, that one. Yeah, it's true. I remember that. It's true. I played that as a kid. It's like brown and white.
Yeah.
So, yeah. I remember that. That's true.
Hmm.
So yeah, what would it take to expand to that? That's just a different state space if it's 2 players, right?
Yeah. Other than that, it's not that complicated.
What about continuous spaces?
Yeah. So the setup is a little different. So then it's like so it becomes, I think, a Markov game or something like that, an MDP game or something.
Yeah.
Where you just, instead of having one action, you have an array of actions for player 1, and then also an action for player 2.
Then even better, continuous action space.
And then you've got and they have a continuous action space. So you've got an array, a collection of continuous actions. Yeah, so it's a bit. But other than that, it's not very different. You just kind of take the whole thing to.
So similar to the things that we've looked at, or that we skipped today, with the randomized squares and so on, to basically discretize your continuous space or whatever you need to do to make your
maybe I'm not so familiar with it. I don't really know.
Fair enough.
So I mean, this could be, the action could be like, I don't know, let's say, so in Pong it's just like going up or down, but what if you actually had the action of like be here, right?
Yeah.
Then this thing is just like 2, so it's basically R2.
Yeah,
So,
yeah.
But like so in all this, what was it like, OpenAI papers.
Oh, I see what you mean. So this would be, your state space would basically be defined by the actions of both players or the positions of both players.
Yeah, so exactly. So so typically the state, the observation space would be the so in this Mujoko environment. So what the OpenAI people did was they just take the full observation space, which included not just your own joint positions but also your opponent's.
Yeah.
So instead of having to do like a visual thing because it's too complicated, they just fed in the internal sort of position and not velocity but position of your opponent.
And so that's similar to when they play, what is it, like Super Smash Bros. And so on.
I guess so. I guess that just both players get to see basically the full, or at least a very big part of the observation space.
Okay. Well, I guess that's what the player gets to see as well, right?
Yeah.
Mm-hmm.
But again, how are you gonna, how would you implement these counters if your state is continuous? So it can't be. It can't be.
No, because then your tree is also not like an actual tree.
So
your tree is like, you've got like a continuous fan of other stages you might propagate into. I have no idea how that works. So,
Because I've never heard of any Monte Carlo tree search implementations applied to continuous problems, either action or state spaces.
Yeah.
I mean, I don't know like how. I mean, you would have to discretize your action space in order for it to even be a tree.
Yeah, because you can't have a continuous tree.
No. So I don't really know how to do it, but I mean, I also just there could be a way. I
Oh
don't
yeah,
know
just
the way of it.
apply this any kind of quantization like tile coding, but then it just becomes infeasible really quick.
Yeah.
Like
Yeah. Yeah.
so what's the conclusion? It's good for games, but nothing else.
Well, does the human brain do it continuously?
I don't
Or
know.
that's the approximation that our neurons use, because they're discrete entities, right? And they only fire at a certain threshold, I think, that kind of thing. So they're not. I don't know how they approximate continuous states with finite computing power, if you will.
I mean, yeah. I also don't really know. I mean, it's hard to.
But like brain, this also has some kind of fine rate. Yes.
Oh, you mean you've got more dimensions that you
So,
can
yeah.
play in? All right.
That's basically how you can detect the source of the noise. But you have just like 2 years.
Yeah.
How come you can detect if it comes from back or front, and then just based on the delay of how sound approaches both your ears, and like this tiny difference makes a whole lot of sense. So yeah, it's temporal frame, it's temporal rate coding, all that matters.
We do a bunch of stuff that, like, it's harder to do with a computer. Like, when you're driving a car, like, I don't know how wide my car is, or like how big a gap is. And I can't measure it with my eyes, but I know if I can fit through a gap. But like a computer, you can sort of measure things really easily. But like I can't do that in my brain, but I can do the next step.
Yeah.
Does that
I
make
think
sense?
your brain can do it. You can't
Yeah, you
consciously
you
access that.
Yeah, I can't get like the distance,
Yeah.
but I know if I can
Yeah.
fit through.
Yeah.
I don't know.
Yeah. And judging by the many damaged mirrors in like that you see when I drive to markets on Sunday mornings, not everyone can access that at all. Yes. Yeah. So that's I think that gives us definitely a route for next time, which I wanted to do anyway. Was I think the chapter 12 is continuous spaces for policy gradients. That is really cool, but I think I wonder whether, like you said, if you start discretizing it, does it get unfeasible, and can you do something different?
Continuous space for policy gradients.
Yeah.
But that's what we've done with the PPO and all that. All of them are continuous.
They just work for continuous.
They just work.
They're designed for continuous, even more like
Yeah.
that.
Okay. But
As opposed to DDPG, for
I'm not
example.
really sure whether I'm thinking of the
BKM.
thinking of the right
Yeah,
thing.
All policy gradients are continuous as far as I know. Initially.
Yeah. I mean, yeah. I mean, I feel like you should be able to also do it for Cube, right?
For Q,
I don't know how, but I feel like intuitively there must be a way to.
I mean, definitely DQM works for continuous. Continuous state space.
Oh, it was
But not the
continuous
actions.
That's what it
When
was.
action space becomes continuous, that's the whole difference.
What if
That's
I
right,
just
that's
have
That's right.
like a stochastic, what if R is just Q is just a stochastic thing, like defined over the action space? So it's something that I can take an average of, say.
Yeah, you could. I mean,
and then,
but then it becomes a DPG. Sort of.
okay. I don't know that's still on my list, I just don't know what that is.
Okay.
What does it become, sorry?
DDPG. Basically, DDPG is a continuous key learning. It's a continuous DKM. Okay.
Okay, cool. Yeah, then I have to read that. I
Is it
don't know.
like dueling the policy gradient something something? Just to understand what's with these.
Deep deterministic policy gradients.
It's a cute learning.
Yeah, it's based on invalid iteration.
Huh. Okay.
Yeah, cool.
Alright. I think.
Yeah, maybe it's good that if at least one of us reads it and then
Yeah. Well, these are relatively short. I should read them next time. I'll have a look at these, and I think I'll also look at Patrick. I'll talk to him. Patrick, I think, did the reinforced implementation of Kung Fu Master or whatever in this Russian course that we did.
Okay.
That could be interesting to look at as well. I'm not sure if it was reinforced or something beyond that. But it was. But yeah, I'll check with him, and then we'll do either this or that, and then we could look at DDPG after that. I think that would be does that sound like a sensible progression?
Yeah.
And then any time after that you've got that you've got your talk ready, I'm happy to.
Yeah, I'll try to do that in a couple.
Yeah. Okay. Cool. And we're perfectly on time because I also do have another engagement in 30 minutes, and then.
Okay, cool. Right. Sorry for the unstructured thing.
No, that was awesome. That was really good. You're on video, so just check out the link on YouTube, and you can link to.
Yeah, that doesn't work.
Yeah, you can't just send your tutor the yeah.
Yeah. Share a couple of videos.
My email?
You have a picture
It's
I'm working in that.
exactly in this kind of thing.
Yeah.
Okay.
And well,
yeah.